of x as x squared minus 4x plus 1. Okay? And so let's get all of our first derivative information. You might say, is there a second? Yeah, we'll learn about that in the next section, 5.2. But for right now, they're just after the first derivative. F prime is 2x minus 4. And we've already talked about how profit is maximized where marginal profit is 0. In other words, we're interested in where the first derivative is equal to 0. So set your function equal to 0. Find the x that does that. Well, 2x minus 4 equals 0. Clearly x is 2. That is your, in this case, one and only critical point. Now, I'm going to graph that point. So in order to graph a point, I need its y-coordinate as well. How do I get the y-coordinate? Take the 2 and put it back into the original f. You don't plug it in the f prime, you'll just get 0 back again. You plug it back into the original because you're after its coordinate, y-coordinate. So that's 2 squared minus 4 times 2 add 1. So is that 4 minus 8 is negative 4, add 1 is negative 3? So that means, so far, here's what we have. So let's scale my axes 1, 2, 3, 1, 2, 3, 1, 2, 3. And so here, when x is 2, y is negative 3, there's the point 2 comma negative 3. Now, that is my critical point and the only critical point. They're one and one only. Which means that this 2 subdivides the x-axis into 2 intervals, to the right and to the left, right? If you have a piece of string and you make one cut, you get 2 pieces of string. So now let's do our shape table. Over each interval, I'm going to test the first derivative to conclude something about the shape. So I have 2 intervals. Left of 2, right of 2. Now, there are some of you who've done this before, and maybe if you did it before, they taught you to write the interval parenthesis, negative infinity, comma, 2 parenthesis. And maybe they taught you to write this interval parenthesis, 2, comma, positive infinity, parenthesis. If you somewhere have learned the purple notation, fine. You don't have to use my notation. You will not have been taught a notation that I haven't seen somewhere before. So, you know, if you learned this before using a little different notation, fine. It's okay. Do whatever is comfortable for you. But if you haven't done this before, I think my way of setting forth the information makes it clear as possible. Okay, now what we're going to do is we're going to test each of these intervals. And we only need to test one point. One point in the interval, because here to the left of 2, it's all going to be increasing or it's all going to be decreasing. It's not going to do both. It's not going to be increasing and then decreasing, because that would create a new critical point. And there is one and only one. critical point. So that's why in each interval, we need but test 1 point. So take any number you want, left of 2. How about 0? F prime of 0. And I'm concerned if this is positive or negative. If it's positive, the shape is increasing. If it's negative, shape is decreasing. Go back and plug it into your first derivative. F prime of 0 is negative 4. It's not the negative 4 that's important, it's the negativity. The fact that it's negative means the shape is decreasing. And now how about F prime of 3? Test 1 point in that interval. 2 times 3 minus 4. That's 6 minus 4 is 2. It's not the 2 that's important, it's the positivity. And so now all you have to do is sketch. And I'll take a different color. So here on the left, I want to sketch a decreasing curve that ends in that critical point. Sketch a decreasing curve that ends in that critical point. Here on the right, sketch an increasing curve starting at that critical point. And you're not at all surprised, because you've learned x squared minus 4x plus 1. You've learned that's a parabola. And you're not surprised. The critical point is the vertex of the parabola. It's the lowest point. It's where the parabola is minimized. Now, as I say, this is just a rough sketch. If you wanted to draw something more accurately, and you won't have to, but if you wanted to, you'd have to plot more points. Like, for example, when x is 0, f is 1, it should have passed through that point there. But you see, I've missed that. So I should, if I wanted my sketch to be more accurate, I'd have to plot more points. But that's good enough. However, in sketching this, I did make an assumption. And we're going to address this assumption in the new material today, in 5.2. I'm going to take my red pen, because the following sketch is wrong. But why is it wrong? That's the new material. So when you sketch this, you could have drawn decreasing. There's a decreasing curve. Increasing. There's an increasing curve. So only based on this for information, you can't tell that the red is wrong. But 5.2, here's what we're going to be talking about today. 5.2, we're going to talk about something called concavity. And what we're going to see is that the parabola is concave up, which is why the purple is correct and the red is wrong. Because you see the purple concave up means that the bowl holds water. It's curving upwards like that. The red we call concave down. If this were the cross-section of a bowl, the bowl would be upside down and it would spill water. So in 5.2, we're going to talk about concavity. And the concavity will decide the distinction between the correct purple and the incorrect red. But we haven't gotten there yet. That's going to be the new material. You know, I've already done the work. I suppose I could tell you I mean, we're right here. The way that in 5.2, all right, this is the new material. The way in 5.2 we'll determine what the concavity is by taking the second derivative. What's the second derivative? It's the derivative of the derivative. If you had 2x minus 4 and you asked for the derivative again, you would say 2. And notice that the second derivative is positive. That's how you know this thing is concave up, when the second derivative is positive. So that's where we're going today. That's the new material. You know, this is the first time we've talked about the second derivative. And today I'm going to talk more about it, but let me, you know, I said that in this day and age when you all drive cars, it's sort of easier to teach calculus because you know in your bones what these things feel like. Okay, so I started way back when talking about the first derivative as velocity. So you know what instantaneous speed is. You're out driving on the highway, you glance down at your speedometer, and the instant you glance down, the speedometer reads 67 miles per hour. You know that at that instant, you're driving at a speed of 67 miles per hour. You all know in your bones what that feels like. Okay. Your first derivative, your speed, is the rate of change of your position. 67 miles per hour, how fast are you going? In 1 hour, you have gone 67 miles. It's a rate of change of your position. Okay. Now let's think about the second derivative. You're out there on the highway, and you're driving a constant 67 miles an hour. You got it on cruise control. You're going constant speed. Your speed is not changing. What if you decide you want to speed up? You want to increase your speed. You're behind the wheel of your car. Physically, what do you do to increase your speed?
Go faster.
Yeah, go faster. How? Mechanically, what do you do to your car? You press the what? What do you call it?
Gas pedal.
The gas pedal. What else would the gas pedal be called? Accelerator, right? So you depress the accelerator in order to increase your speed. Do you see why acceleration is the second derivative? It's because you want to increase your speed. You want to increase your rate of change. So you depress your accelerator, 70, 75, 80 miles an hour. You have accelerated. Your rate of change of your rate of change, right? Second derivative. The rate of change of your rate of change is increasing. Okay? Your radar detector, your fuzz buster goes off. What do you do if you want to slow down? Hit the brake. Because that decelerates. So when you want your acceleration to be negative, when you want to decrease your speed, you hit the brake, you decelerate. Okay? So today we're going to be talking about the second derivative. And you know in your bones what the second derivative feels like. The second derivative is the rate of change of your speed. It's the rate of change of your rate of change. If the second derivative is positive, you are accelerating, your speed is increasing. If your second derivative is negative, you are decelerating, you're slowing down, your rate of change is getting less. Okay. So hold that thought. Let's take a look at number 15. F of x is, x cubed plus 3x plus 1. X cubed plus 3x plus 1. Okay. Let me leave some room here for my graph. Yeah. So I'm going to put my picture here. And so let me come down here and let me do my first derivative stuff. I take the first derivative, it's 3x squared add 3. Agreed? 3x squared add 3. And I want to set that equal to 0. Okay, be careful here. How do I want to explain this? This nowhere equals 0. And how can I convince you of it? X squared is always positive. X squared might be 0, but it's not negative. And you're adding a positive number to it. Do you see that no x would satisfy this? What if you attempted to solve it? Maybe if you attempted to solve it, you'd have 3x is equal to negative 3. So if you tried, maybe you'd move the positive 3 to the right. Maybe now you'd divide by 3. Divide by 3. And you come with x squared equals negative 1. Oops. No x will do that, right? No number squared would be negative 1. And so there are no critical points. And so if there are no critical points, there's only one interval, right? So I want to do my shape table. I have intervals over which I'm going to test the first derivative to conclude something about the shape. And I only have, if there are no critical points, if you have one piece of string and you make no cuts, you have one piece of string. You have only one interval, the whole real line. And so, let's find out. We only need to test one point. Let's say 0. F prime of 0. Put 0 in for f prime. You have 3 times 0 squared plus 3. 3 times 0 plus 3 is equal to 3. It's positive. So therefore the shape is increasing everywhere. And so far, that is all you can do in 5.1. So when x is 0, f is 1. So there's a point on the curve. And so you know that this thing is increasing everywhere. As far as you know as yet, if you just drew a straight line, that's all you could tell at the moment. curve increasing everywhere. But now, this is a good problem then to go on to what color shows up. Yeah.
Wait, where do you get the 0.01 from?
Oh, you're right, I had no critical points, right?
Yeah.
So I need 1 point to hang my hat. So I picked a point,
Oh, okay.
because I need to put it somewhere. Because I didn't have any critical points. Normally I'd plot the critical points, but I didn't have any. And so this thing is increasing everywhere. And this is a good example to go on now. You were not asked to do this in this problem. But this is a good problem as to why we have to have the second derivative. If now we take the second derivative, here's the original f, here's the first derivative, we take the derivative of the derivative and we get 6x. And we set that equal to 0 to get what is called the inflection point. Solve for, this is called the inflection point. And let me see if I can make that understandable. 6x equals 0, the only value of x that would make 6x 0 is x equals 0. So there's an inflection point at x equals 0. Okay? You're out in your car. You're traveling a steady 67 miles an hour. You decide you're going to speed up. So you accelerate. You start going faster. 70, 75, 80, 85. And then you decide to slow down. You take your foot off the accelerator and you depress the brake. And you know what that feels like, right? When you're accelerating, you feel this in your bones. When you're accelerating, you know that you are being pulled forward. When you hit the brake, you don't want to hit it too hard, right? Because you feel, when you decelerate, you feel yourself being pulled back, right? So, from positive acceleration, going forward, hit the brake, decelerate. Where your acceleration changes, that's called the inflection point. You've gone from pushing forward to pulling back. So that's where your acceleration goes from positive to negative. That's where the second derivative is 0. Before it was positive, after it's negative, where 0 is where you hit the brake. So that's the inflection point. And so what that means is now we can do, and I grant you, this is new material, this is 5.2. Now we can make a concavity table. Just like we made a shape table, now we can make a concavity table. We have intervals over which we now are going to test the second derivative. Because if the second derivative is positive, concave up, you're increasing. Negative, you're pulling back. Concave down, decreasing. And that'll tell us something about the concavity. Now notice we do have one inflection point, which means we've got two intervals, right? If you have one piece of string and you make one cut, you get two pieces of string. So you have an interval left of 0, you have an interval right of 0. And so left of 0, take any number you want. Again, concavity is not going to change. If you're over here on the left, you're not going to go from concave up to concave down because that would create a new inflection point. And there's only one. So there's one and only one. And so let's take f double prime at -1. Here's f double prime. Put -1 into the second derivative, you get -6. The point is that it's negative. Your concavity is negative. So you're pulling back and it's concave down. Let's pick any point to the right, f double prime of 1. That's +6, it's positive. You are positively accelerating your concave up. And now we can finish the sketch. This is increasing everywhere. But left of 0, it's concave down. What does increasing concave down look like? To the right of 0, it is increasing, but concave up. Okay? So that's how you put this information together. And does this sort of make sense? Do you remember, I mean, like back in high school, did they have you graph y equals x cubed? Do you remember that the simple cube curve, it looks like this? Did you see that graph in high school? You see the similarity? This purple is just the blue shifted up by 1. So you're not surprised at the purple shape. But you see why you need concavity to tell the whole story. Because if it weren't for concavity, the following is wrong. I mean, if all you knew was that it was increasing, you might think it was a straight line. That straight line is increasing, yeah, but it doesn't have the concavity. So now when we're doing these problems, and we do this, and these are your instructions in 5.2. In 5.2, you have to have both tables. 5.1 so far was only asking for the black. Let's take a look at 21, which is similar. 21 is very similar to the number 15 we did, only instead of plus 3x, it's minus 3x. Notice how that's going to change things. So here we have f of x is x cubed minus 3x plus 1. Okay. So I'll draw my graph here. I'll wait a minute to scale my axes. How big does my y coordinate has to be? I don't know. I'll find out in a minute. Okay, so I want all of my first derivative information. I want all of my first derivative information. So f prime is 3x squared minus 3. Okay. That makes a difference. Because now when I set this equal to 0, I've got some actual critical points. I don't care how you solve this. Factoring is usually a good idea, but I know most of you would probably just move the 3 to the right, divide by 3, x squared equals 1. So there's nothing wrong with that. How do I want to write this? Let me take another piece of paper. Because most of you would probably proceed this way, and it's fine. So 3x squared, you'd move the negative 3 over to the right-hand side. You'd divide by 3, x squared equals 1. You know there are two possibilities. X could be negative 1 or positive 1. Nothing wrong with thinking like that. But it does help if you can factor. What I'm saying is, this left-hand side, can you factor it? Can you factor a 3 out? See, I'm leaving the right-hand side alone. Factor out a 3. And now, can you factor a difference of squares? X squared minus 1 is x plus 1 times x minus 1. You get to the same place, I know. But factoring will come in handy in more complicated problems. So for right now, if you did it that way, fine, no problem. That's great. My point is that there are two critical points. X could be negative 1 or x could be positive 1. So remember, I need the y coordinates because I'm going to plot these points. Go back to my original f. Don't put the negative 1 back in f prime, you'll get 0. That's where it came from. Put the negative 1 back into the original. That's negative 1 cubed is negative 1 minus 3 times negative 1, add 1. So that's 3 minus 1 plus 1 is 3. And here, when I put 1, I get 1 plus 1 is 2 minus 3 is negative 1. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So when x is negative 1, y is 3. There. There's a critical point. And when x is 1, y is negative 1. So I have these two critical points. Do you agree that gives me 3 intervals? It's 2 and only 2. 2 and only 2. There aren't any others. That's how you can test your intervals. So if I've got 2 critical points, don't I have 3 intervals? If you have 1 piece of string and make 2 cuts, don't you get 3 pieces of string? So here are your shape intervals. So I have 3 intervals. So left of negative 1, between negative 1 and 1, to the right of 1. And so I'm going to test 1 point in each of these intervals. Pick any number left of negative 1, let's say negative 2. And is that giving you a positive or negative number? So far, this is an easy problem. You could go back to here if you want. Negative 2 squared is 4 times 3 is 12 minus 3 is 9. The point is it's positive. Soon the factoring form will be easier, because if you put negative 2 in, that factor is negative, that factor is negative, negative times negative is positive. But whatever, the first derivative at negative 2 is positive, so your shape is increasing. Now pick any number between -1 and +1 out with 0. Put 0 into f prime, you get -3. It's negative, so your shape is decreasing. Pick any number to the right of 1, say 2, you get +9 again, so it's increasing. So you know that your graph is looking like this. Left of -1, it is increasing. Between -1 and 1, it's decreasing. To the right of 1, it is increasing again. But can you see that I'm cheating? I have drawn this, and it's drawn correctly. This is concave down, this is concave up. And it looks like our inflection point is at 0. But concavity is the next section. So for right now, problem, largest interval increasing, decreasing, relative max and minimum. Oh, I hadn't been saying that, but I guess it's clear. Notice that this critical point, this is a relative minimum. Right? It's a minimum because its y-coordinate is shorter, less than all its neighbors. But it's not an absolute minimum, because way over here on the right, the thing is plunging down to negative infinity. So this has no absolute minimum. So there's no absolute minimum. Some books say global instead of absolute, and I might slip and say global. It means the same thing as absolute. Likewise here, at 1, 3, this is a relative maximum. Because its y-coordinate is taller, higher than all of its neighbors. It's at the top of the hill. But there's no global max, because this is just getting larger and larger and larger and larger. So there's no absolute or global maximum. And as I say, I'm cheating a little bit, because we will learn in 5.2 that this is concave down on the right. And in 5.2, we'll learn this is concave up. I misspoke. Concave down on the left, concave up on the right. Okay. So at this point, the following is wrong, but without concavity, you wouldn't know it's wrong. You know, if you had sketched increasing, decreasing, increasing, the red has the same increasing, decreasing, but the red is the wrong concavity. But you don't know that until the next section. Let's see. I had a thought. What did I mean to say? Oh, well, I forgot. Let's take a look. Number 25. So here we have f of x is equal to x to the fourth minus 8x squared, add 3. So I'll leave room for my drawing here. So now let's get our first derivative information. F prime of x is 4x cubed minus 16x, right? 4, old power, new coefficient, new power is 1 less. 8's coefficient, it stays. 2, the old power's coefficient. 8 times 2 is 16. Minus x, new power is 1 less. Derivative of 3 is 0. Now, here's an example where I think factoring is more convenient. You want to set this equal to 0, and I want to suggest factoring. Do you see you got two terms? Can you factor out of 4x? They both have a common factor of 4 and of x. You're left with x squared minus 4. But now, isn't that a difference of squares? So you have a 4x, you have an x plus 2, and x minus 2. And if you set that equal to 0, do you see that you have 3 critical points? There are 3 values of x that make that product 0. The idea of factoring is the only way a product is 0 is if one of the factors is 0. So either that is 0, or that is 0, or that is 0, which is how you find 3 critical points. Okay, if I do these in order, x could be negative 2, x could be 0, x could be positive 2. And I need the y coordinates of all of these. So take that negative 2 and put it into the original. So negative 2 to the 4th power is 16 minus, well, negative 2 squared is 4, that's 32. Add 3. So negative 16 add 3 is negative 13. When x is 0, y is 0 minus 0 plus 3. And here for 2, notice I've already done the work. Because when I put in negative 2, these powers were even. So it's still 16 minus 32 plus 3, negative 13. So I need to plot these 3 points. So because my y coordinate's bigger, let me scale the axes differently. On the x-axis, let me say 1, 2, negative 1, negative 2. And on the y-axis, how about 5s? 5, 10, 15. Negative 5, negative 10, negative 15. So at negative 2, I have negative 13. Right about there. At negative 2, I have negative 13. And when x is 0, y is 3, right about there. and when x is 2, y is negative 13. Okay? So we have 3 critical points. Give us 4 intervals. Always one more interval. So here's your shape table. We have intervals over which we're going to test first derivative to conclude something about shape. And we're going to have 4. So left of negative 2, between negative 2 and 0, between 0 and 2, to the right of 2. So let's try negative 3. And here is where the factored form really is easier. All I care about is the sign. I don't care about the magnitude. So put in negative 3. That factor is negative. That factor is negative. That factor is negative. If I multiply 3 negative numbers together, don't I get a negative number? My shape is decreasing. Now how about f prime of negative 1? That factor is negative, but that one's positive. And that factor is negative. So negative times positive times negative is positive, it's increasing. F prime of 1. Positive, positive, negative. That product is negative, decreasing. F prime of 3. Positive, positive, positive. Product's positive, it's increasing. And so, let's do it. You are decreasing on the left down to there. Then you're increasing on the right to there. Then you're decreasing to there. And you're increasing there. There's your graph. Notice I'm cheating my concavity. I know that over here I'm concave up. I know here I'm concave down. And I know over here I'm concave up. But we're not going to learn that until the next chapter. But you can see why concavity is important. It tells you how your curve is bending, how it is bowing. So you can finish off 5.1 and start looking at 5.2 for Wednesday. See you Wednesday.